Hello. Hi, guys. I'm going to just hit the road running. Uh, Welcome to our presentation titled True Story, How Rust for AArch64 Linux Became a Tier 1 Target Platform. Um, the This is a joint presentation between me and Florian. I'll do a brief intro later. And the intent is to kind of course, do a slightly historical kind of take on what it took to get to Tier 1. In the hope that other architectures, other target triples can also benefit. And also, of course, to kind of like showcase the strengths and weaknesses of the technology here and what our plans are moving forwards. So without further ado. Right, so by way of quick introductions, Florian is a very well-known Rust developer and trainer. He's the co-founder of Ferris Systems, a name synonymous with actually ARM, embedded ARM kind of support in various tools and even the Rust language itself. He's also a board member of the Rust Foundation, newly created, and he's a part of the community team. I'm Robin Randhawa. I'm a longtime friend of Linaro's. I've been at ARM for way longer than I thought I would stick around for. I work in the open source software group, and my focus areas are safety-themed software architecture, specifically for automotive, industrial, and robotics domains. So let's jump right in. What's the big deal with Rust and why should anyone care? Now there are many different ways of explaining this. I wanted to share like kind of my own personal experience here. So if you're talking about systems programming and if you're talking about performance software and popular software, C is your mainstay. You can't avoid it. The design intent and general philosophy with C was maximal code portability, fine-grained control over machine code data and layout, right? And maximal performance, as close to the metal as you can possibly get. And to achieve this, C assumes an abstract machine model. There are lots of material literature on this. And by design, it permits a level of intentional ambiguity in the language spec. So that intentional ambiguity was useful because it enabled near absolute control of the underlying machine, right? Why? Because machines are different. And if you want to maximize what you can do with the underlying machine, you need to kind of be able to tinker with that difference, right? So, and it actually gave rise to this, C is the assembly of higher level languages meme, which I actually subscribe to. But there are a number of problems. Code safety had to take a backseat if you were willing to expose the innards of your underlying instruction set architecture and the microarchitecture to the programmer. So there were type size ambiguities. There were, can you use a pointer as an integer and the calamity that can ensue kind of ambiguity, buffer, overflow, underruns, use after free. You can Google this stuff. There's lots of it, right? So basically, this put the onus of writing safe code on the programmer. And that became a significant problem, especially if the projects were large. And once you hit Moore's law and once things like Amdahl's law kind of started becoming critical because things needed to scale out, then concurrent and parallel programming was intended to be the norm. It still isn't actually as much as one would like, but it became C's kind of philosophy became a problem there. So in order to rationalize things, languages evolved differently, right? So you had dynamic typing, garbage collection, all of these things. And that was great. It enabled kind of programming without being very, very particular about safety. But there were trade-offs, right? So what ended up happening was that C became dominant in kind of the so-called system software layers of the stack. This is all very subjective and people might differ on definitions, but firmware bootloaders, hypervisors, kernels, that's where C became dominant, where, you could kind of do with the control. And people who were writing high-level apps, banking apps, high-frequency trading, web servers, they didn't want to worry too much about the capabilities of the machine to that extent, right? So they wanted flexibility. They wanted like something where they can focus on the algorithms and not on the nitty-gritties. And that's where all of these high-level languages became predominant. But the trade-off over there was you couldn't really use them in areas where you would use C, like if you're writing an operating system kernel, for example. So, and then Rust came along, and I will justify what I'm saying over here, right? But basically, the claims it made were like, we'll give you compile time static analysis of your code. We'll give you guarantees of memory safety. Oh, and by the way, we'll do that even when you're doing concurrent or parallel programs at compile time. And we'll also consider the synchronization practicalities, right? And I was like, okay, I don't believe any of that, but let's check this out, right? So just jumping ahead a bit, like Rust is probably the only programming languages that is intended to be primarily a systems language, but because of its unique take on safety, it's actually used in the full stack. Okay, so here's an example that Florian put together, which demonstrates things. This is Rust code. You have a vector, which is like a sequential collection, and it's mutable over here. You have a reference to one of the elements in the array. You attempt to add to the vector. You attempt to add something to the vector, another integer. And after you've done that, you try to print what you added through that reference. You might think this should just work. What's happening over here is that the first time you get this allocation, when you do a push to it, the system might need to reallocate because it may need to kind of allocate more memory to satisfy the push that you want to do to it. And in C or C++, specifically C++ in this case, because I've seen this happen a lot over there, it would allow you to do that without complaining, except that you would then have an invalid reference, right? So the Rust compiler over here will just simply prevent that. It'll say that, you know what, it's got a notion of usage of memory from an ownership standpoint. And it actually keeps track of what memory has been borrowed for use by what context, what scope. And over here, it will call out the fact that, hey, you've sent out a reference to this to another scope, and then you're trying to do a print with it later. I won't allow that. This may seem innocuous, especially to advanced programmers, but this is actually a very, very common problem. Synchronization. This is interesting, right? So in C, the tendency is that if you want to have some shareable, mutable data that you want to share amongst different software execution contexts, like pthreads, for example, or processes, you kind of end up using a synchronization primitive, but there's no explicit coupling between the synchronization primitive and the data that it's trying to synchronize accesses to. So you have problems like forgetting to take a lock, right? And you won't see that problem immediately in most cases. You'll see it when it's too late. So how does Rust prevent that? It associates the data. In this case, here's another collection, a vector of unsigned 8-bit types. And it associates that vector with a mutex, right? And just by doing that, you firstly made sure that nobody can access that data without involving the synchronization primitive. Significant part of the problem solved, right? But as Florian points out, firstly, you ensure that this function, this lock and write function, can interact with the mutex but not manipulate the mutex itself, right? And the ownership tracking design makes sure that the lock will be released before the end of the function, so you can't forget to release it, right? And there is this thing called inner reference tracking. In this case, there's an inner reference involved with the mutex, and it'll make sure that a reference to the lock data cannot be held longer than the lock, right? This is all amazing stuff for somebody who's actually worked with the realities of C and C++ at scale. So there are some hidden gems which people don't talk about actually that much. So the memory safety promises extend even to concurrent settings. So if you have concurrent accesses, the compiler can detect when synchronization is necessary, but more critically, it can also detect when it's not, right? Wouldn't you want to have the comfort cushion of knowing where your intended use of a synchronization primitive is no longer needed? Wouldn't that be cool? Because that should result in performance in the general case. So yeah, so Rust detects when unsynchronized read-only data, access is safely possible. So people don't talk about the strength of like finding bugs earlier in the process, right? The later you go into the pipe, as in development, testing, validation, release, deployment, etc., the later you find these problems, there's an incrementally larger cost associated with it, right? So which is why it's kind of important to find these bugs sooner. And sure, you can do that with C and C++ if you actually rely on all the excellent tooling, Valgrind, the SAN collection of different types, static analysis and more capable compilers. But people don't do that because that's extra rigor. So having a tool that actually forces this at the compile stage itself is pure gold. So I found this like cheesy in the beginning, but I've kind of begun to appreciate it, right? So Stack Overflow does its surveys, and yes, you might dismiss them, but fundamentally, it's interesting to note that Rust has been the most beloved programming language for 5 years running, and there's a lot of detailed literature available on what beloved means in the context of the surveys done. But the resonating theme is that it just makes it easy to do things that were considered very hard previously. There's something to say for that, right? Anyway, that was the whirlwind kind of intro thing to Rust, and now let's talk about the real meat of the problem, which is the tier 1 attainment, right? So at ARM, my boss at the time asked me to look at overlaps between open source software and safety critical domains to see where open source software can be used. That turned into, hey, look at all of these proprietary microkernel based stacks. These are the kind of like the top of the ladder, and look at the proprietary ones with due diligence, and then look at the open source ones, and then find out what we can do. And that also actually extended to looking at programming languages, and I spent a fair amount of time looking at Ada and Erlang because they're languages synonymous with safety and security. That experience led me to build a kind of a subjective, you have to start somewhere, subjective view of merit of these languages, right? So I came up with what anyone would do, which is build a tabular representation of technical aspects, right? Like what specifically is there to promote safety and security? Memory safety is rampant, right? You'll see numbers being quoted by Microsoft and others, like 70% of all known vulnerabilities are to do with memory safety. What explicit support does the language have to protect against that? Can it do that in concurrent and parallel scenarios? Does it straitjacket the programmer, or is it expressive? And how rich is it? I mean, is it batteries included or not, right? And why were these technical aspects important? Because there are real problems with kind of solving some of these with the standard kind of systems programming languages today, right? And I'll speak about some of that later. But the critical ones were the other aspects, right? Safety and security is such an important thing these days that if you're writing software for any application domain and you're not designing in upgradability by default, if you are not seriously considering using open source by default because it will give you an upgrade path, then you're asking for it, right? But can languages cope with that kind of a model? What is the development model? What is the governance model? Do I have to join an ISO committee? Do I have to pay money? Can I express a design intent for the language and have it succeed in the implementation? Or do I have to do things by the high priest method, right? What is the community dynamic? Is the language likely to become niche, or is it likely to be general purpose? Does it have a following? Is there evidence of ecosystem uptake? Those kind of things. So I then kind of like Rust came along on my radar because of similar kind of safety and security kind of stories. It actually came to my plate because of AutoSAR, which is another story. But anyway, I started looking at it. This is the Rust language logo on the top left, and that's Ferris the crab. That's the mascot on the bottom right. The Rust ecosystem makes a big deal about metal, and Ferris is a play on ferrous, and ferrous is iron. Anyway, so I spent some time evaluating the language's claims, right? You can go to that link and see where I've gotten this stuff from. So yes, the literature says, Rust is blazingly fast and everything. It allows you to do reliable software development, and it's great for productivity. And I came up with my own kind of intent to qualify all of this stuff, right? So for benchmarks, right, it's a hard one. How do you compare languages? Micro benchmarks are available. There is a community maintained, not Rust community, general open source community maintained set of benchmarks called the Computer Language Benchmark Scheme. Decided to have a look at that. This analysis is on AArch64, Rust versus C, but we are doing similar analysis with AArch64 internally, and I saw that yes, Rust is at par. Micro benchmarks are micro benchmarks. You need to understand them, but you can't dismiss them either. From a macro perspective, the closest I could find was like this web server framework shootout. I replicated these results internally as well, and it was quite compelling to see that feature matrix wise and performance wise, Rust implementations have something going for them. Productivity tools, like the compiler really gives you an really respectable amount of hinting about what's gone wrong, and you have to experience this to realize what I mean. Over here there's a misnamed variable and you get a lot of really good guidance, and depending on how much you're willing to dive in, it'll give you some surprising amount of help to try and resolve issues, right? So yeah, the tooling was looking very good. I've always had a problem with C and C++ is packaging, modularization, distribution kind of story. There's this tool called Cargo that Rust has that does all of this stuff for you. It's kind of built in that sense. It'll invoke the Rust compiler for you. It'll create a directory with metadata for identifying the code, for licensing the code, specifying dependencies in a versioned way. So, reproducible builds and license checking across dependencies, these are all built in, which is really useful. These days, especially when you're dealing with really complex code bases, you need as much help as you can get from the tooling. And this is really interesting project called Rust Analyzer, which has really revolutionized the kind of like IDE story, right? So I use it with Vim, and it's brilliant. It'll give you code context on hover, hinting, it'll do automatic refactoring, etc., etc. And these things matter, especially in this day and age when there are less of us dinosaurs around and there's more of the younger crop. Now, I won't go into all of this, but there are lots of other things that Rust brings which are really worthwhile. So generics, when you want to get the compiler out of the way because you're willing to take the risk that you have an unsafe escape hatch. Cross compilation is like a first class thing and not something you have to bodge around. And embedded domains are carefully considered as a target, right, in most projects. So lots of really useful stuff. If you want to do complex algorithms with optimized sequences, maps, binary trees, hashes, that's all there in the standard library. But then I discovered gaps, right? So AArch64 Linux out-of-box experience was poor. It wasn't bog horrible, but it was poor. And it was kind of sad to see that, there's no non-x64 target at tier 1. And Rust had a top-class language reference. It still does, of course, but there was no ISO-grade language reference, and I saw that as a bit of a problem. So I first did some bridge building after I had done my own evaluations. Alex Crichton, a very prolific Rust developer, put me in touch, who understood the problem space well and was also advocating for ARM to reach tier 1 in some target triple form. He put me in touch with the Rust Lang core team. Josh Triplett from Intel back then pointed me at the tier classification document that he had written, and then I had a nice series of debate with them. The core team listened to the pitch I was making and were willing to help. They actually set aside a lot of bandwidth at my disposal, for which I'm very grateful. I got invited to RustConf in 2019, where they put me in touch with kind of my counterparts in Microsoft, Intel, Mozilla, AWS, and Google, right? And that's when I began appreciating how much the ecosystem is already investing in this language. So we had the tier classification story. Tier 3 is essentially official builds of Rust are not available for that target triple. Tier 2, there are official binary releases provided, but automation is not complete, right? And you kind of have a guarantee to build story, but not necessarily like completely comprehensively tested, right? With tier 1, you get the full shebang. There's full automated testing. Every release goes through this. The Rust compiler test suite is run to completion, etc., etc. Lots of assurances are extracted. So my assessment of the problem was that if I want to pull this off, I'll have to do all of these things. I'll need to get 100% pass rate for the compiler. I'll need to have all of this going on native AArch64 silicon. I'll have to make the silicon accessible to the Rust core team. CI, we'll have to have community-facing experts for ARM and ARM Linux, and we'll need a process for triaging, resolving issues, evidencing all of this using the excellent, well-documented RFC process that the Rust community has, then kickstart the process of feedback, iteration, and working with the team to finalize releases. In short, I couldn't do this alone. So I started building Mindshare at ARM. It turns out people are looking at Rust pretty much everywhere. And there were people in my own open source software division, but also in the compiler tools in the research division, who are all using Rust, mostly in a semi-formal personal capacity. So I created a special interest group, and it was hugely popular. That was the first step in the Mindshare building process. The second was me, and I have to give credit where it's due, Rodolphe, a friend and one of my mentors at ARM, who was a fellow conspirator in understanding the value here, because he cares about safety as well. we both kind of made a pitch to our Lord and Master, Mr. Hambleton, who I'm sure many of you know. And true to him, he understood the value over here, and he said, all right, let's get some engineering resource for you guys. So we had a small team. So what did the team do? The compiler test suites are extensively documented in Rust, right? So it got about trying to do cross builds, native builds, do triage of failures. All of us were helping with this with elbow grease. Fix-ups, upstream submissions, and engagements with the community to merge this, right? This is an ongoing thing. For Silicon, I figured that the best thing would be to provide a bare metal cloud server. I managed to find something that with a reasonable spec, and I managed to make a pitch to the bean counters as appropriate inside ARM and enable access to this. And there's this fantastic person, Pietro Albini, in the infrastructure team in Rust, and also a member of the Rustline core team, who kind of pretty much helped us understand how to set up the CI loop from scratch, right? There were significant problems with GitHub from a privacy angle. Pietro fixed them. We helped in. Kushal and Ed helped with all of the paperwork and provisioning the silicon. The core team set us up with a ARM focus group kind of infrastructure. So Zulip is the kind of communication tool of choice that the Rustlang community uses. So we had a private ARM tier 1 channel where we did all of the correspondence. And then there was a public one created called T-Compiler ARM, where all of us from ARM would be present, and any questions, etc., any triage, we would help over there. So a Triage Bot was set up, which is like the system that if anyone files an issue, we get a notification, and then we very quickly work with the community to triage that. So yeah, I did my first RFC submission on the 17th of July. The RFC process was very well documented. There are links available in this presentation. And it basically was a pretty long kind of RFC document. And I had to provide justifications with evidence for all of these, right? So a report that all the tests are passing, with history where they had failed and how we had done, all the outlining the necessary support infrastructure, including the dedicated hardware, evidence that the CI is working as expected, long-term viability, and of the target-specific ecosystem. Some slightly subjective things over here, which I try to defend as best as possible with the empirical evidence that I had at hand. So all of that kind of worked well with a lot of support from the community. And there were issues, but most of them were to do with fundamental education awareness about ARM architecture, etc. One of the big issues was, there were some tests that were written historically to have a particular kind of assumption about ARM, about x86, and we had to kind of like do a massive crowdsourced initiative to look at all the tests and classify them. Everything worked out well in the end. And then there was this massive blocker, which was the AArch64 LLVM backend doesn't have generic support for stack probing mitigations against stack clashing. And I thought, at this point, okay, we're kind of screwed. But again, credit where due. Christoph, a friend at ARM, senior person who looks at toolchain stuff, put me in touch with Linaro. And I want to make a special mention over here of Oliver Stannard, who actually helped prioritize resolving this. And now this feature is well underway. And then, yeah, there was the final RFC submission, unanimous vote in the end. Ultimately, the vote closed, and we finally had Rust being announced as available in Rust 1.49 on December the 31st, before midnight UK time, interestingly. And I was very pleased, and I drank a lot of whiskey. Some fundamental things over here that Florian pointed out, that tier 1 is obviously important, but tier 2 also has to be taken seriously because it can be a release blocker if there's something pretty fundamental over there. But of course, tier 1 is the highest assurance, and it influences the quality of tier 2 and others. So what was the important thing that came out of the tier 1 attainment? It's kind of put focus more critically on tier 1, and there are a lot more people looking at this stuff now. Yeah, Florian will tell you that a lot of people have now come to Ferris Systems saying that we want to work with Rust on ARM because we have assurances. Now, there are other gaps, and I may not have time to go through all of this, but this is an ambition level to look at various technologies with the communities, industry, the Rust Foundation, others, to try and look at the lower layers and put Rust to work over there. So things like making system software easier, firmware, bootloaders, operating systems, etc. And there's this plan to take Rust to ISO 26262 deployment, which involves the Ferrocene program from Ferrous Systems. I urge you all to look at the details. It's quite interesting. And we've got some plans for futures and outlooks as well, in terms of what we want to do over there. So I think I've run out of time now, but I've kind of covered everything. If anyone has any questions, please reach out to me at any point in time. That's me.
There's questions in the chat.
Okay.
We can go through and answer a couple what we still have
Go for it.
time. Okay, I'll go bottom to top. There's one question from Cyril Rubis. As far as I can tell, cargo is supposed to be installed by piping output from curl to shell. How are the practices like this supposed to work together with building more secure applications? You're probably referring to the toolchain manager RustUp. And RustUp is generally shipped in a lot of Linux distributions as a package itself. So on those distributions, you can just avoid that. Install RustUp, and then RustUp has a secure channel to our toolchain backend. So if curl to shell is not your thing, we generally provide that as instructions on downloading the setup tooling there. If your Linux distribution ships a package for RustUp, I recommend using that one. There's a question from Timothy Cersei. Do you think the strict rules of the compiler will help open source projects, particularly Linux and Rust, to allow less experienced contributors to help, or would it have the reverse effect by making the C programs run away? I'm not sure if I would frame it this way. First of all, C is going to go away at any time soon, especially not in kernel space. Rust brings a number of things to the table also in conjunction with C. So for example, the mutex interface that you looked at earlier is built on top of usually operating system provided mutexes, which are often implemented in C, but gives additional safety guarantees on top of that. And I don't see any of those effects. Also, I think one thing that's frequently forgotten in these discussions is there's a lot more to these kinds of developments, like understanding how the machine works, understanding how the hardware works, how all those interactions work, than just the programming language. And that is often a little bit underrated. Here's one question around, is Rust going to get a stable ABI? The current static link everything, because no defined ABI is a big problem, especially in the distro world. The problem with the here is mainly that Rust as C++ rolls out generics and templates across libraries, and that is hard to constrain in an ABI. Rust supports the C ABI, so you can build a dynamic library that is linkable, dynamically linkable, or a static library for that effect, in any kind of host program, and that looks like a C library. So you can, so the stable ABI currently is the C ABI if you want to rely on that, or the systems ABI. I know people are thinking about that. I know Swift has added a stable ABI at cost of at runtime cost. That is actually quite interesting and something that we follow. And then there's a funny question from Andy Shevchenko about what if you need to lock few data from different objects, probably on the mutex example. So the things that the mutex example shows are not particularly to the mutex implementation, but rather language features that were used to implement that mutex interface. So different locking strategies would then use different primitives in the back. There's also the standard library ships read-write locks and all kinds of other implementations that use the base language features to give those safety guarantees. So in your case, different primitives and different strategies would work as well. But the important part is that you cannot hold references to the inner data once you unlock the data again. So you cannot escape from this. It's the crucial part.
I see that Masson is planning to run away from Rust, or already has, which is fine. I should point out that we need to stop looking at the world in absolutes when it comes to the value prop here. I've learned this the hard way. I would encourage you to as well. There's no perfect solution. If there's anything that's marginally better, it's a good thing. Thank you. That's us.